So let us try to have a continuation on our compound bars. But this time we need to focus when it is a condition where the bars are placed in series. Remember in the previous case, they were in parallel, and we had conditions there for a parallel combination, same as a series, depending that with the number of bars that you are given. Let us just consider a basic illustration that maybe there is a bar that is here, then another one is also connected in series. These two, they are different in presentation, definitely. They are going to have different lengths. If this is A and this is B, we are going to notice that A is going to be having its own length, its original length. B is going to be having its original length. And it's because of the extension, we are going to have or obtain an extension at B. And A is going to be having its own extension, change in length, a series. By just noting this, we can see that in the series, these two lengths are not the same. The length for A and that for B. A is on its own, B is on its own. They're not the same. They are not the same. So what is it that you're going to consider to be the same? It is the force. Remember that if we consider a force being applied this way, the force here is the same as the force here. So that part is the same. The extension, A has got its own, B has got its own. It's not the same. It's no longer the same. So in series, we can conclude that since we saw that the extensions are different, so the total extension, it is no longer to say it is A equal to B. No, it is the sum of these two because they are not the same. One at A and that at B. It is different like what we had in a parallel. When we extend the same way. The length is the same. This one is different from that. So meaning to say we can have this as XA plus XB. Extension, change in length at A plus the change in length at B. We can have that way. As we saw that the change in length previously, we're using the formula force times length into area over area times E like this. Remember this formula when you're using this. So with this formula, we can make adjustments from this. We can make adjustments to say therefore X total is going to be XA, which means we're going to have FL, A like this, which is at A plus that at B plus that at what? At B. The change in length at A, the change in length at what? At B. That is what it means. We are no longer having like what we had in a parallel, guys. And noting that we are in a series where the force is actually the same. So you can conclude here Since in series, the force is the same, meaning to say, as you are considering your total force, you take the force at A, or you can take the force at what? Force at B is the same. And the Young's modulus is also the same. The Young's modulus for A is the same as the Young's modulus for B. So we can conclude that in this formula, since these two are the same, the force and this force is the same, the Young's modulus at A and the Young's modulus at B are the same. So we can factor these two, which are the same, the force and the Young's modulus. So it does not, this part does not care to say which force are you taking from, which Young's modulus are you using is the same. So you remain with length over what? Length over area. Length over area plus here again, if you remove this, you remain with length over area, the length at B over the area at B. So we can have this formula in something that is understandable this way. Since the force is the same and the Young's modulus of elasticity is the same. So questions, they differ with what you're given, but these are some of the things that you need to know. And as we do understand that if we are working with the stress that is going to be at each point or each material, if it is the stress at A, you need the force at A over the area at A. That one for B also, the force at B over the area at B. But knowing that these two are the same. So like I said, depends on the situation, the condition of the question, the area, that part. But this is what you need in a series. The fig that we see here in fig 1.48 shows two round steel bars connected in series under a tensile force F. Under a tensile force F, where the maximum stress brought about is 110 megapascal. The maximum stress, 110 megapascal. If the maximum stress is given as 110 megapascal, okay, where is it? The maximum stress actually happening? The maximum stress, it occurs on a section or the bar that has got the smallest cross-sectional area. The smallest cross-section by looking where we have got, this is like the cross-section. This is a bigger cross-section. This is a smaller cross-section. So this is where our maximum stress happens, where there is a smaller section. So there are two things to consider, this section and this section. So you're going to call it 1 or 2, or you can call it A and B. It's up to you. So we are given to determine the final change in length, our xt, the final change in length, the total. That's the whole of it. Provided that E is equal to 200 gigapascal. Remember, E is the same. E for A is the same as E for B. So that's why we're just given that one. So remember, we need to calculate the total, which we can have from either this presentation or this presentation. Okay, so if we work it from a simplify this, we can take this way. We saw where it came from. So guys, I don't think that can be a challenge to grasp. I don't think that can be a challenge. Xt is equal to what? That is F over E. Okay, so we're going to use that as F over E like this into what? LA over the area at A plus LB over the area at B in a simplified part so that you do not work so many things. Or you can just use that other one. It's just one and the same, guys. Just one and the same. So the question is, are we having all these? The force is the same. F that we are talking about there is the same as the force at A. It is the same as the force at B. We do not have that. So we do not have this. The E we are given. The length at A, we can check from A, the length is given. Length, we have it. At B, the length is also given. So the length, they are there. The areas, they are not there. We do not have the area. At A, we are not given. We do not have the area at B. We are given their corresponding diameters. So there is a need for us to calculate the force. There is a need for us to calculate the area. We saw that in the calculation of the force, they will need us to work with area. So it's best for us to start with working with what? With the areas first, because force needs us to have area. In order for us to have the force, we need what? The areas. So let's start by calculating the areas. The area at A, it's a circular part. You're given the diameter. That is 25 millimeters, our diameter. In meters, divide by 1,000, that's 0.025 in meters. So you can have the diameter, just use 25 times 10 to the power of minus 3. So the area at A from pi d squared over 4, the diameter at A. That is pi times the diameter at A, this decimal, or you can just write as 25 times 10 to the power of minus 3, the millimeters. So this is d squared over what? Over 4. So that was going to give us area at A, or just area 1. You can call this 1. All right, so this was going to give us decimal. That's 0.00 490,873, something like that. Okay. This is your area in square meters, which you can just have it as 1, 2, 3, 4. Can even use 6, 4, 5, 6 up to here. 490. 490,87. This is going to change into a 4 times 10 to the exponent of -6. Think we are used to that, guys. Okay. We have got our area. At B, we have the diameter, so we can do the same. Pi d squared over 4. But the diameter at B now. So we're going to have pi times the diameter at B, 20 millimeters. 20 times 10 to the exponent of -3 squared. We can just have it as a decimal. So that was going to give us the area at B, and this as a decimal. It was going to give us, that's a lot of zeros again, 0.003, 141,592, something like that, square meters. So using 10 to the exponent of -6, you can count 1, 2, 3, 4, 5, 6 here, which is 314,159 times 10 to the exponent of -6 in square meters. Since like there's a lot of calculations to be made, and to the exponent of -6, it makes at least our calculations to be a little bit within the range, like because of that rounding off. Remember, guys, you're rounding off, you're rounding off, you're rounding off. So just use anything that you're comfortable with, but too many zeros, you can even use -4, you can use -6, okay, which is fine. With these, we can now try to find the area, the force, because we can see that what is limiting us here is what? The force now. Areas, they're now there. We now need the force, which you said it can be the force at A, it can be the force at B. So what can we use now to find the force? What is it that carries the force? It is the stress. within the stress, we know that there is a force because the stress is given as what? Remember? Now we need what? The force. So remembering that the stress is equivalent to the force over the area. But there we are not just given any normal stress. We are given the maximum. This is the maximum stress given. Where does it occur? The ultimate stress. On the section that has got a smaller section in presentation A. So meaning to say, the maximum stress, like I was saying, it is affecting the part at what? At B. This is at what? At B. So if it is at B, we can use the force at B and the area at B because that's where the maximum stress is. So what will be the force at B? Just have to cross multiply. So the F at B cross multiply is the area at B times the maximum stress. We calculated this area at B, remember, from what we got here. This is the area at B, 314,159 times 10 to the exponent of negative 6 times the stress, the maximum stress of 110 times 10 to the exponent of 6 megapascal. So it was going to give us the force. And this was going to be 34,557.49 Newton, which you can just write in kilonewton, divide by 1,000, which is 34,557 kilonewton. Okay, so this is the force that is at B. If it is the force at B, therefore it is the force also at what? At A. Remember, this is the same. So this is our total force. So with this information, guys, we've got everything. Now the total extension, the total change in length can be calculated. Force over our Young's modulus. What is our force? Calculated this 34, this. Then the Young's modulus 200 gigapascal. You are given that. Just have to substitute into the formula now. So the first 34,557 times 10 to the exponent of 3 over our Young's modulus. This was 200 gigapascal times 10 to the exponent of 9. Into what? Length over area. Length at A, area at A. That is why we had to calculate these areas. Length is given already. Length at A, the 900 millimeters that we are seeing there, 90 millimeters, I mean. So we've got the length 90 millimeters times 10 to the exponent of 3 over the area at A. The area at A, we calculated this. It was 490, comma, 874 times 10 to the power of minus 6. So you have got this. Then we can add length at B from our diagram again. It is there, 110 millimeters. So that's 110 times 10 exponent of negative 3 over the area affecting at B. Calculated this also. 314,159 times 10 to the exponent of negative 6. As it is like this, it is going to give us the total change in length, total extension, the final extension, the final change in length in meters. So that was going to be 0,0004 of them. There are 4 of them. Then this is 9218 in meters. So you can just write, guys, 1, 2, 3, 4, 5. Or we can even use whatever that you want, guys. So it can be given as 9,218 times 10 to the power of minus 5 in meters by the millimeters. Okay, it's up to you the way that you write your answer there later on. But we have got change, total change in length. The total change in length. So it is of the question that you are given. What are you dealing with? What are you working with? How is the presentation there? The part of the series is not going to change. In series, what is it that we have? Force is the same. Consider our extension. We must add because each has got its own extension. Same as what we're given on this question, the bar shown in Fig 1.59. Here's a maximum stress. So the maximum stress is 215 megapascal. Where does it occur? Where we have got a smaller section in terms of the presentation. This is where we have got the smaller section. So the maximum stress is going to affect the middle part here. That's where our maximum stress is going to be. Remember, there are three sections. This section, this section, this section. This is what we have. It must carry a tensile load, of 180. That is the tensile load. We are given the force this time. Total force we are given. Okay. 215 megapascal. The force we are given 180 kilonewton. Remember, this force is the same. In series, the force is the same. Same as force here, same as here, same as. So you're going to name your points. Is it A, B, C, or you can name them 1, 2, 3. So it's the force at 1, force at 2, force at 3. It's the same. Causing a total extension. They gave us the total extension this time. It is causing a total extension of 0.18 millimeters. The total. They gave us. Calculate the length of the middle portion given this E. The length of the middle portion. So in terms of the length, we can see that we have got this total length, this one, the 230 millimeters, which is equal to 0.23 if we divide by 1,000. And we are given this piece, the length of the last part here, 50 millimeters divided by 1,000, that's 0.05 meters. This is the section that we have. The middle part, we do not have the length here. The middle part, we do not have its length here. They want you to calculate its length here. Calculate the length of the middle portion. We do not have this. So let's just call it L2, the middle part. The first section here, we also do not have its length. Here, we do not have its length. So since they want us to calculate the length of the middle part, which is L2, let us have this section, the first section here, its length L1. Let us have its length in terms of L2 because what we need is to find, remember, what we need is to calculate L2. So let's remove L1. Is it possible for us to write L1 in terms of L2? Because our answer is supposed to be L2 that we need. So can we write L1 in terms of L2? Is it possible to write L1 in terms of what? In terms of L2. What does it mean? The length of the first section here is going to be equal to what? Remember, we're given, guys, the total length of the whole section is there, this one. So it means we are going to subtract 0.23. We remove what from there? So for us to remove with this part here, this length, what are we going to remove? We are going to subtract the length of the middle section. We are also going to subtract the length of the last section, the third section, the 0.05. So this is going to represent in terms of L2, the length of the first section. Okay, so let's subtract 0.23 minus 0.05. Those are like terms. We're going to get 0.18 minus L2. So we have written L1 in terms of L2. This L1 that you are seeing, the length of the first section here, can be written in terms of L2 as what? 0.18 minus L2. Okay, this is where we are. It means each and every section has got its length, its original length. This is the original length. Each and every section has got its original length. So how are we going to have this length L2? Which formula consists of the length? We saw from the extension, because we are given that. Why are they giving us this? The total extension. Let's analyze from there. From xt, our total extension, we do understand from the previous formula that I stated that we can have it this way. It's up to you. Or you can have this way. So I'm going to use this way as the last one, which is where we factored up the f over e into what? Since there are three sections, guys, this time, remember this was supposed to be what? I want us to be careful. I want us to be very careful there. It was supposed to be LA over A, LB over length over area of what? What you're given. Here there are three sections. So it's going to be length over area, the length one over its corresponding area. So it's L1 over its corresponding area plus the middle section, length 2 over its corresponding area. The third section, its length over its corresponding area. This is what the extension is telling us. Where this L1 here, remember, it is now written as what? 0.18 minus L2. So it means with this formula, we were going to calculate L2 because there is L2 here, there's L2. Why calculate L2? Remember L2, guys, we need what? The middle section, the middle portion. That's the one represented by L2. Or you can use whatever that you understand. You can write it in terms of L. So we need to calculate L2. So this formula, L2 can be calculated. L3, the length at the last section there, we are given. Okay? The total extension, definitely, that is the one that we have here. The total force is given. The E, we are given this E. If you take a closer look there, you're given the E. So on this formula, what is left? The areas. We do not have area 1. We do not have area 2. We do not have area of the third section. Area of these three sections is not given. The area of these three sections are not there. They are not given. So thus, we must calculate these areas. So that's your strength, guys. Strength of material. You don't have this. You find this. Your formula is missing this. You find your formula is missing this. Like that. It's like that till the last topic where the formulas are to be used. You just have to be careful. So let's calculate our areas. All right. So here, we have it on the diagram. Not gonna here. We already wrote it. Just gonna erase this because we're gonna have a lot of things here. So let's calculate the areas. Calculate the areas. All right, the area at the first section. The first section, what do we have? There's a diameter there. This is a presentation of a diameter, 60 millimeters. This is the diameter of the first section, 60 millimeters. So area can be calculated pi d squared over 4. So that is pi times the diameter, 60 millimeters, 60 times 10 to the exponent of minus 3 squared over 4. So you're going to have the area of the first section. Those zeros again, 0.00282743338, like that, square meters, which there are few of them. So you can even use times 10 to the power of minus 3. 1, 2, 3. There are few there. So you're going to just take 2,827 times 10 to the exponent of minus 3 in square meters. So the area of the first section is there. The second section, the middle section here, the middle portion, we want its area, but we do not have the diameter. We do not, it was a circular part. We are supposed to be given the diameter, but we are not given that diameter. So what are you going to do? We are limited there. We do not have anything. But remember what I said about this maximum stress. Where does it happen? In the section that has got the smaller section according to the presentation. This is where we've got a smaller section. So that's where our maximum stress occurs. So using that and the force, because the force is given, remember the force is the same. Are we not going to be able to calculate the area? We can, because the stress, it has the force on its own inside. So here we are going to calculate the area at 2 using what? The maximum stress. That is the section with the smaller or the smallest cross section. The smallest cross section in terms of your presentation is at 2, the middle part. So using that, we do understand that stress is force over area. So meaning to say the maximum of this is going to be force and area at 2. So you can calculate the area at 2. Make this the subject. You're going to cross multiply. Area at 2 times this maximum is equal to F2. Then we divide by what? By our maximum stress given there. That was going to give us the area at what? At the second point. So the area at the second point was simply going to be taken from F2 over the maximum stress. That was the condition. Where we do understand that it's a series, the force is the same. This is force 1, this is force at 2, this is force at 3. So the force is the same. 180 times 10 to the exponent of 3 over the maximum given stress of 215 megapascal. We're going to have the area there. Just like that. So the area, guys, was going to be given 0,008372 093, something like that, in square meters, which you can have or write as just gonna consider 1, 2, 3, 4 up to this point, 8,372 times 10 to the exponent of -4 in square meters. Or you can use the exponent of -6. It's up to you. So you calculate each and every area. Area at 1 is there. Area for the second part is there. You need the area of the last section, area at 3. The last section, there's something that you are given. They gave us that it's a 40 by 40 millimeter square cross section. It's a square. So the area is the area of a square. In millimeters, convert to meters, divide by 1,000, 0,04 meters times 0,04 meters. It's a square. So you use the area of a square. So the third section, that is a square there, side times side. You're just using whatever that you're given there, 0,04 times 0,04, remember, in meters. So that we get what? The square meter. So use the one in meters. And our area was going to be 0,0016 square meters. Just like that. So you can even write as these powers times 10 to the exponent of, or just leave it like that. This is where we are. Remembering what our question is all about, we need to calculate the length. We need to find what? L2. The length of the middle section, the middle portion. We need to find L2, remember. So with this formula now, we have got F. We calculated these. All is there. So you can substitute and try and manipulate and solve this equation until we have our L2. Solve the equation now. So let's substitute xt. We are given that. Because this extension, because of these lengths that we are talking about, the extension is supposed to be in what? In meters. So we are supposed to write this in meters. 0, 0.18 millimeters means 0, 0.18 times 10 to the exponent of minus 3. It is equal to the force. Remember the force you're already given. 180 times 10 to the exponent of 3 in kilonewton over E. What is our E? We are given 208 gigapascal. Our E is given 208 times 10 to the exponent of 9 into what? You substitute now. We are supposed to substitute L1, but we cannot substitute L1 because you'll be having a lot of unknown values. That's why we have to write L1 in terms of what? In terms of L2. So L1 in terms of L2, remember we got this as what? 0, 0.18 minus L2. We are writing in terms of L because we need L2, guys. So you must write in terms of L2. In terms of what you are supposed to calculate over area 1. The first part is area. Remember, we calculated this 2,87, right, as it is. 2,827 times 10 to the exponent of minus 3 plus L2. This is the one that we need to calculate. So we're just going to write as it is, the middle portion over the area of the middle portion, area. When we calculated, this is what we got, 8,372 times 10 to the exponent of minus 4. The last section, L3, we have it. So you cannot write in terms of L2 because it's there. 0, 0.05 meters in meters. So that's 0, 0.05 in meters over what? The area of the third section, which is this one that we got, 0, 0.0016. We have to substitute everything that we calculated. Everything that we calculated into the formula like this. This is where we are. From what you're given, because we're given extension. So they want us to use that extension. So we need to calculate L2. Remember, that's our part, L2. So what are we going to do now? Let's get rid of this because it's under a multiplication, this one. So you can simply cross multiply by this, then you divide by 180. So you're going to multiply 0, 0.18 times 10 to the exponent of negative 3. You multiply to this denominator as it is, 208 times 10 to the exponent of 9. Then whatever that you're going to have at this side, it has to be divided by 180. So you have to divide by 180 times 10 to the exponent of 3. So by doing this, we have removed this. So what is going to remain if you remove? There is going to remain a 1, like a 1 here. So means a 1 times this bracket, it is the bracket that is, it's going to remain this bracket as it is, guys. So if it is this bracket that was going to remain, what were you going to do? You were going to take this side because there is equal to this side as it is. So you're going to take this side so that it subtracts there. It's a positive. So you can transpose that so that it can be subtracted. The 0, 0.05 over what? 0, 0.0016. Take it there. There's nothing to do because there's a 1 that is left there. So on the left, on the right-hand side now, this side, you are left with these 2, which are carrying what? Which are having L, where L is here. So you must separate. Let's start with the first fraction here. So you must separate this way, this over this. You divide. Okay? Must divide. This one over this one on your calculator. 0, 0.18 divided by 2,8, whatever that we have there. It was going to give us 63,672. You do the same thing where L2 is. It's minus 1. So it's minus 1 divided to this. We are now separating. Remember, guys, minus 1 over this. So it was going to give us minus 353,732. But there is what there? There is L2. Remember, you divided this, but there is L2 there. So you must indicate L2. So that's we have separated this part here. This fraction, there are two terms here. So you take this to the denominator, the remaining part over the denominator again. Then this part, there is L2 over this is same as 1 over this. So divide this 1 over this. What are you going to have? It is going to give us a positive. It was going to be 1,194,458 L2. Just like this. So this is where you are. As we can see from this side, that there is a need for us to simplify our left side. There's a need for us to simplify the left side of the equation. Or with this, we can simply take this to the left side again because it says there is no L2 here on this one. So as you simplify this, combine this, guys. You combine this, everything like this. After that, subtract this 63,672. Subtract it also there. You are going to get 113,078, which is equal to, definitely you've taken this to the other side. So on the left-hand side, you'll be left with these two. On the left-hand side, you'll be left with these two. So you combine these two terms that are left on the left-hand side. You combine these two. That is minus this 353,732 plus 1,000. And add those two numbers. You are going to obtain 840 like this, comma, 726. But there is what? There is L2. This is where we are. And we need to calculate L2. So what can we do? Simply divide by this. The number that you're given there. 840,726. 840,726. So this can cancel. And you're remaining with L2 there, which is the length. The one you are being asked there. The length of the middle section was going to be 0.1345004 like that. As you know that this length will be in meters. All these dimensions that we are working with will end up in meters. Yes, we can do the conversions up to you later on to convert to millimeters. Just multiply by 1,000. So the moment you multiply your answer by 1,000, it was going to give us 134,504. Okay. That's a 0 there, like 1, 2, 3. That's just 1 0 there. Just check, guys, on your calculators what you're obtaining there. What is it that you are having? But it's supposed to be multiplied by 1,000 for you to have the millimeter concept. The millimeter concept. So it is your calculations. Whatever that you're given there, are you able to work with that in order for you to get the required measurement, the required length, whatever that you have? Are you able to work with that? Try by all means to understand your basics from the diagram that you are given. Understand your diagram. Lengths, how are they presented? Understand that. So this is what we had, guys, till we meet again.